Okay, now we're going to start the next unit, which is polynomials. We were going to do some factoring, but we're going to say factoring for tomorrow. We'll do factoring on Friday, which makes perfect sense. Factoring on Friday. In any case, we're going to get into polynomials. So polynomials are the sum of terms where x is raised to a non-negative integer power. You can't have fractional powers. You can't have negative powers. They must be positive. So they're positive, but they can also be zero. Basically they're saying the last term can't, or the first term, a sub n can't be zero, or it's not x to the n. So anyway, if you look down there at our examples of polynomials, you'll notice that for the first one, notice this is x cubed times x times, and there's no x there, but we know those are polynomials and they allow for a constant term right there. But the way you look at it is, see, this is x to the first power and this is x to the 0 power. That's allowed. So they say that it's non-negative. It can be 0 because that's the constant term. So whenever you have the constant term, which is that's a constant, that's still a polynomial because that's x to the 0. Now for this next one, it looks funny. It looks like something's wrong with it. Well, it's not really. If you just take this and break it into two fractions, all they've done is put it under the same fraction. If you rewrite it, and you rewrite it as 2/3 x, let me erase this so you can see what you're doing, and then it's minus 1/3 x squared, doesn't matter. Like, the coefficient can be fractional. The coefficient can be anything. Well, number. But notice that's a power of 1 and that's a power of 2. Those are non-negative, so it's a polynomial. The next one is a factored polynomial. What you have is 3 terms. And if you distribute this is going to be x cubed. I can see it's x cubed. The way I do it really quickly, let me show you real fast, is we just do our FOIL trick. This is x squared. This is negative 6. This is negative x. This is plus 6x. So we end up with x squared plus 5x, and then it's minus 6, which is clearly a polynomial because we have an x squared term, an x term, and a constant term, which is the x to the 0. Now, for the next non-polynomials, notice for this I am dividing by x, and I can't factor it out because if I factor it out, I've changed the function. I've removed the whole. So this doesn't count as a polynomial because we could rewrite this. We rewrite it without you don't factor stuff out. You just rewrite it. And we have 5x to the 4th minus x squared times x to the negative 1. And that's what's not allowed. We can't have that. No x to the negative 1. That's a negative. So we can't have it. So that's not a polynomial. Over here, we rewrite this as x to the 1/2 power minus 16. And we're not allowed to have fractional powers. So that's not a polynomial either. All right. Once we've established that we have polynomial terms, we can describe them. The degree of the polynomial, which is really important. In fact, right now my calculus kids are having to face that in their AP questions. They talk about we're using polynomials to represent transcendental functions like sine, cosine, inverse cosine, inverse tangent, exponential function, natural log, things like that. And the degree, because we have to write a representation, the degree is that highest power, the polynomial term that has the largest variable component, the value of especially the x. So what it's saying is the exponent. So it's whatever degree it is, it's x to the n power, where the degree is n. So in our example, like the first one, that was x cubed was the largest power. So this, right here, this is a degree of 3. It's a third degree. Polynomial. This one is a second degree. Oops, it jumped on me. And we're going to get into the importance of all that later on. We're learning how to describe polynomials. I've actually been dealing with them for a while, but we need to take it to the next level now. Then there's leading coefficient. Leading coefficient. Basically, it's the coefficient of the largest exponent term. So x to the n, this would be a subscript n of x to the n, where the leading coefficient is that number. So if we look up in our first example, -5 is a leading coefficient, and what we write that is we go L period C period. We just abbreviate it that way. Leading coefficient is -5 for this. For this one, that's this one. Hang on. That one, the leading coefficient is -1/3. For this back one over here, leading coefficient is 1. It is, oops, second degree. And you are describing the polynomial. And when somebody tells you've got a second degree polynomial, you understand what that means now. All right, we've been doing end behavior for a while. And we need to talk about how end behavior is controlled by the degree and the leading coefficient. So not only can we describe it, but by understanding the degree and the leading coefficient, we can figure out the end behavior. All right, we're going to start with things you know. So we're going to draw x squared really quick. So you should be able to draw it really fast now. It's at 0, 0, 1, 1, 2, 4. And then the rest of the points are off this grid. We'll just draw it in. Notice what's going on for my end behavior. As x approaches negative infinity, y approaches infinity. As x approaches infinity, y approaches infinity. Right? So notice, for both of them, both go in the same direction. Everybody see that? It goes in the same direction. They both go up. And notice it is an even power. So we're doing even degree, meaning the power of the leading coefficient, or the largest coefficient, or the largest the term with the largest exponent, that exponent is even. And if we look at this, if we look at the leading coefficient is 1. So the leading coefficient, actually I think I used blue for this earlier. Let me keep using the same color. So leading coefficient's 1. So our leading coefficient is 1, which is greater than 0. It's positive, so it's greater than 0, meaning it's positive. That means that these are going to go in the same direction. So this is the same direction because it's even. Actually, let me write that in red because we did that earlier in red. Same direction. The even tells me same direction. The positive tells me both are up. They're both going to positive. It's both up. Let's look at another polynomial. Negative x squared means I've reflected it across the x-axis because it's all the way on the outside. So now it's 0, 0, -1, -1, -1, -1, 2, -4, -2, -4. There's our parabola. didn't do a very good job on that one. I lost my point. There it is. Helps to have something to aim for. Now notice what's happening this time. As x goes to negative infinity and infinity, this time they both go down. They both go to negative infinity. Notice my degree is even, so that means they're going to be the same direction. And look, they are. They're both the same direction, right? And then my coefficient here, it's a -1. So my leading coefficient is -1, which is less than 0, which means it's negative, so it's going down. They both go down. All right. So that's even. Then there's odd. And you know what even means. Even numbers are 2, 4, 6, 8, 10. Odd numbers are 1, 3, 5, 7, 9, on and on. All right. Now we're going to do a cubic. You learned these when you did Algebra 2. So the points for the cubic, the parent function, and we've gone over it when we did when we did functions. So 0, 0, 1, 1, and then 2 cubed is 8, so it goes like up here. And then 1 cubed, so -1 cubed is -1. -2 cubed is -8, so it's like down here. And it looks like so. Okay, as x goes to negative infinity, this goes to negative infinity. As x goes to infinity, y goes to infinity. Okay, you already knew that, but let's look at this. We have, this is degree, this is third degree, which is odd. And notice, with the odd ones, it's like a line. They go in opposite directions, right? So for when it's odd, the end behavior is opposite. So for this, they're going to go opposite. Notice what happens. These are going opposite, aren't they? Opposite direction. And that's because it's third degree. And then our leading coefficient for this, leading coefficient, is 1 again, which is greater than 0, which means that it's going to have a positive slope, which means it goes up from left to right. So it's a positive slope. And when I talk about slope, I'm just talking about as you're moving from left to right, it goes up. So let's look at the other. So everybody understand that one? Let's go to the next one. For our next one, we're going to do the negative, which means we reflect across the x-axis. So we've got 0, 0, but instead of -1 going, -1 being -1, it's -1 is +1, because -1 cubed is still -1, and then you have another negative, which makes it +1. But +1, and you cube it's 1, and you make it negative, it makes it -1. And then the next point is 2 at 8, and 8 this way. So it has the opposite slope. Notice as you read from left to right, now it goes down. Let's go through it. Third degree. If it's odd, it means they are going in opposite directions. As x goes to negative infinity, y is going to infinity. As x goes to infinity, y is going to negative infinity. And we see these are opposite directions. And our leading coefficient is a -1, which is less than 0, which means my slope, as I read from left to right, is going down. Notice it's going down from left to right. And that's true for every polynomial. Every polynomial, you can decide if it's even or odd based on its term, the term with the largest coefficient. Let me go ahead and summarize this. So for even functions, the end behavior is that you have the same direction which means that both are up or down. For odd, the end behavior you have opposite behavior. One goes up and one goes down. Okay, so now that we've got that, we can go in here and we can make a little table that basically summarizes what we can look at. We can look at a polynomial and we can get a general shape every single time. So if we have a polynomial that its leading term is positive, or leading coefficient is positive, and it's an even degree, then as x goes to negative, well, for basic shape, they're both going to go up or both going to down. So this means the same. Then the leading coefficient is positive, which means it's going to go up on one side and it's going to go up on the other. Which means that no matter whether you're going to negative infinity or positive infinity, the y is going to go to infinity because it's going to go up, because they're going to go in the same direction. If your leading coefficient, so this is basically what I'm leading coefficient is positive for this one, leading coefficient is negative for this one. And for this one, if the leading coefficient is negative, it means that it's concave down. It opens down. Yeah. And y is going to go to negative infinity for both of them. Not behaving. There we go. That's better. It still looks horrible. Let me try that again. There we go. That's better. Y is going to negative infinity for both because it is even. And then there's when our leading coefficient is positive. Oops, wrong thing. Positive and negative, but now it's odd. So for the odd, then if it's positive and it's odd, then it goes from, as you read from left to right, it goes up. So that means from the, it's called the inflection point. It looks like a cubic. But it can be any odd number. And then if it's a negative leading coefficient, then it goes down as we read from left to right. So it goes up from that direction and down. And you look at the overall trend and it's a negative slope. And that means that if it's doing this, then as x goes to negative infinity, then y is going to negative infinity. And as x goes to infinity, y goes to infinity. For the one that has a leading coefficient that's negative, means you're going to reflect it across the x-axis, then this one, y is going to positive infinity as x goes to negative infinity. and y is going to negative infinity as y goes to, as x goes to positive infinity. Okay, so that's the first thing we can do. We can look at it now, and without touching a calculator and without graphing any points, we can get a general shape of it. So you can answer those in behavior questions without ever graphing it. Then there's zeros, and those are the where we're gonna factor it, and we're gonna set it equal 0. Now we know how many zeros there are going to be based on the degree, because at most the number of degrees, or the number of zeros, is at most the same number as the degree. There can be fewer because we can have duplicates. And I'll show you what I'm talking about that. You may get it more than once, but you'll get the number of places, when you factor it, the number of factors is the degree, because you have x cubed. If you have x cubed, you're going to have 3 factors, or at least you're going to have, when you multiply it, you get, you'll show it. It's not necessary 3 factors. At most 3 factors. Anyway, you'll see what I'm talking about. It's easier to explain. It's easier to show you than explain it to you. Okay, so multiplicity means that you have the same solution twice. For instance, remember when you would factor it and you get x plus 1 times x plus 1? That means it's x plus 1 squared. It means that the solution x equals to negative 1 happened twice. So that's what multiplicity is. It's when you get the same factor twice, so you get the same 0 twice. And the multiplicity, it defines the shape. So think about x squared. X squared has two factors. It's x and x, and so they're both equal. The solution, the zeros are 0, but there are actually 2 of them. That tells you something about the shape. So basically, if there's one multiplicity of 1, which means you essentially have like x plus 1 times x minus 2. They have a power of 1. Each of your factors has a power of 1. So we don't write the 1, but they all have a power of 1. Well, then that behavior, the shape is called a cut. Well, that's how we describe it, a cut. And for that, it just crosses. It just crosses the x-axis. That's what that 0 looks like. So a line's obvious choice, right? And then cubics work that way. No, cubics don't. I take that back. There are other functions that work that way. We'll get there. I'll show you in a minute. And then there are things called bounces. So a bounce, it's like x squared. Parabolas bounce, which is a quadratic. So whenever you have, like you had a graph and the quadratic didn't cross, it just touched only at one place. Because remember, when you have a quadratic, you can have 0, 1, or 2 real solutions, roots. So what if you have a parabola like this? That's a bounce. It has the same, but if this is 1, then what's going on is we have the factor x minus 1 squared. We have 2 of them there. That's what that bounce means. And so that parabola there, what it's saying is that it has 2 solutions, but they're the same thing twice. So what a bounce looks like is that it comes down, touches the x-axis, and goes back up. And then there's what we call a wiggle. Yes, I know, it's a wiggle. A wiggle is like a cubic. It goes up, and it just doesn't cross it. It's not just straight across. It kind of wiggles across it. So that's the place where the 0 is. It's like a cubic. This is like a cubic. And it wiggles across it. It's like, specifically, it's the parent function for cubic. Like x cubed. It only crosses once, but it doesn't just go straight across. it changes, and the way I described it, it changes concavity across it. It's concave down on the left, and then it's concave up. So it kind of comes up, and then, so that's the root, and then, so I'll put in the x-axis and the y-axis. So it kind of slides across that, and it changes concavity there. All right, so here's an example. We're going to find all the zeros and the multiplicities. So for each one of these, this has already been factored for you. That's why we're saving factoring for tomorrow. So for each one of those factors, you would set it each factor equal to 0 to find the zeros. The trick here, the nuance you haven't seen before is, notice this is squared. And then this is cubed. It means it has that 0 2 times and then 3 times. So in reality, that x squared is just x times x, and x equal to 0 if you set it equal to 0, x equals 0, that's where the root or solution is, and that point for this one, if you put in the 0 for the overall equation, that's at the origin. So there are 2 of these. So that solution, this x equals 0, happens twice. And the twice is due to the square. Then there's x equal 1. For this one, x equals 1. If you put in 1, the overall solution is 0, because it's a 0. Remember that it's a value you can put in. The whole point is these zeros, if you put them in, the y is 0. And there's only one of those. It happens once. And then there's this one where we set x plus 5 equal to 0, so we get x is equal to negative 5. This happens 3 times. And the point for it is negative 5, 0, because it is a 0. If I plug in negative 5, the whole thing will be 0. All right, now you're going to try h on your own. And so you should pause it if you're listening. Try it on your own, and then we'll go through it. So I'm assuming you've paused, and I'm going to go through here and go, oh, that's factor of 4. That's a power of 4. That's a power of 1. That's a power of 5. That tells me how many of those solutions there are. Well, x plus 1 means that for this one, x is equal to negative 1. It's going to happen 4 times. And the point is negative 1, 0. For the x minus 2, this is x equal to 2. It happens once. And that point is 2, 0. And for our last one, this is x equal to negative 3. It happens 5 times. And the point is negative 3, 0. So when you go and think about the graph, go back to g of x, the first one we did, twice means it's going to bounce, once means it's going to cut, and 3 times means it's going to wiggle. For h of x, 4 times means it's going to bounce, once means it's going to cut, and 5 times means it's going to wiggle. And you get a feel for what the shape's going to look like. Turning points are places where you're going up, you're increasing, and then you're decreasing. So you're changing. So remember we did this before where we were talking about the increasing intervals and decreasing intervals, and to change directions you have to pause momentarily. So basically turning points are where the curve is going up and then the curve is going down, and that point where it changes direction is a turning point. And the trick here is that all minimums and maximums occur at a turning point. You're either going up and go change direction to go down, or you're going down and you change to go up. And if we have factored it completely, we know the zeros, then we know that turning points, the maximum number of them at most, is at least one less turning point than the number of zeros. So it tells you what can happen. as far as mins and maxes and the way to sketch it and draw it, because what it's saying is the number of extreme values, the number of extremes, I'll write values. There's a plural for extreme values. It's called extrema, but we'll say extreme values just to keep it simple right now. The maximum number of extreme values, that means mins and maxes, is always less than the degree, less than or equal to the degree minus 1. So a cubic has no more than 2 extrema, 2 mins and maxes. It may not have any. Like the parent function for cubic doesn't have any, but there are other cubics that do. All right, so now we have a polynomial here. And from this, we're going to write down some information and we can get a feel for what this thing looks like. So we look at for degree. When you look at the degree, you got to go find it. Sometimes they don't put them in order, but notice that's the fifth power. That's the maximum exponent, so it is 5th degree. The leading coefficient is the -7, so that means it is negative, right? Which means, okay, I'm going to write down what it actually is. It's -7, which means that since this is odd and -7, it's going to go down from left to right. That's what that tells me right there, just looking at it. That tells me it's going to go down. And then the maximum number of zeros. If it's 5th degree, then the maximum number of zeros, we did that up here, remember? We wrote that down. Yes, at most the same number as the degree, right? So the most number of zeros it's going to be 5. Oops, I should put that in red since it's the same thing. Zeros is based on the degrees. It's 5. And the maximum number of turning points is 1 less than that. So that's 4. And then the end behavior. Because it's a 5th degree and its leading coefficient is negative, I know that the overall direction it's going, I know it's going like this. So I know that as x approaches negative infinity, hang on, I need to write that a little different. Let me make it bigger. As x goes to, make it a little thinner. There we go. As x goes to negative infinity, y is going to infinity. It's going in the opposite direction, starting up and going down because of the leading coefficient being negative. As x goes to infinity, y goes to negative infinity. All right, now we're going to do the next one. And my question is that a I was supposed to check this before. Determine if it's a polynomial first. Is that a polynomial? If it has a -2? No, not a polynomial. Cross it out. It's not a polynomial because you can't have that. No negative exponents, right? That's not a polynomial. For the next one, they're all positive, so we're good. So it's degree, and you got to be careful because, look, we were tricky. It wasn't the first term. You got to look for all of them, and the degree is 6. And for that degree, its coefficient is a +1. So if I know the degree, then the maximum number of zeros is the 6, and the maximum number of turning points is 1 less than that, which is 5. And then there's end behavior, and my end behavior, since the leading coefficient is positive and the degree is even, then I know they both go in the same direction and they're both going to go up. So it's going to go up, both sides. So that means that as x goes to, I didn't go to the thinner one. As x goes to negative infinity, y is going to infinity. As x is going to infinity, y is going to infinity. So you can describe the overall shape of it anyway. All right. So you have a worksheet here where you're going to fill this in and you're going to do a little bit more. You're going to go backwards a little bit. So basically you're going to go to the graphs, and you know what zeros are. So you're going to identify the zeros and you're going to go backwards to try to do polynomials. So I want you to try that. And then this is all insurance in case I have to administer the English test. And then on Friday, we'll go over this and make sure you all understand it. So now go try the worksheet.